So thank you, Bharadwaj. I think it has been very interesting and exciting 11 weeks of discussions on various aspects of quantitative methods in chemistry, and I'm also very pleased by the extent and the diversity of the coverage of the topics that we could achieve in the last 11 weeks. So we have been summarizing this week what all we learned in this course, and for week 4 our focus was mainly on introductory statistics, and how we can utilize a variety of statistical tools for hypothesis testing. So this is very important because we realized in this week that the random fluctuations in our measurements can often result in the measured values being very far away from the mean value of the data set, and we need to apply statistical tools such as the z-test when we know the population standard deviation, and the t-test, which is also known as the student's t-test, and we discussed that it was developed by William Gosset, who gave it for dealing with small samples. So the t-test is applied when we have and usually in our day-to-day lives we will be dealing with the t-test just because typically the number of samples that we deal are finite, and in those cases t-test turns out to be a more appropriate test to be undertaken for testing our hypothesis. We also got introduced to an important concept of null hypothesis, and how we can apply the t-test to test whether the null hypothesis holds true. And we talked in terms of the confidence level. This is a very important concept that we also got introduced to. So the confidence level will in turn decide the confidence interval, and our inference or the results will change based on what confidence level we are talking about. So a null hypothesis can be true at, say for example, 95% confidence level, but it may not hold true at a higher or a larger value of the confidence level, and vice versa. So it is very important to keep in mind the concept of confidence level and also the degrees of freedom when we are testing the various hypotheses. And it is here that we also understood that while testing the hypothesis using these statistical tools, we can commit variety of errors, basically two types actually. So one is the type 1 error, which we call as the false negative error, where we reject the null hypothesis even though it is supposed to be true. Similarly, there can be a type 2 error, which is called as the false positive, where we accept the null hypothesis when it is actually false. So these two errors are to be kept in mind when we are undertaking the hypothesis testing. So I discussed in the week 4 lecture 2 a problem where we said that a disease has a prevalence of 0.1%, and in this disease a certain analyte would come out of range or have a low value than the normal reading or normal range. And we realize that this normal range is defined to often cover 95% of the population. So when we say that reading is having a low value, what we are implying is the left tail of the Gaussian error profile is our region of significance. Now I have been thinking about this. So essentially what we imply here is that about 2.5% of the population will show an abnormal low reading. So what we figured out in that problem was that if we see that out of the people who show this abnormally low reading, which is 2.5% of the population, only 0.1% are actually having the disease. So this implies that only about 4% of the people who have the reading of the analyte low will actually be having the disease. So I have been thinking about this in the context of the recent times where we know that a viral infection is spreading rapidly, and consider that actually this disease has a prevalence of 0.1% in the human population, and we are screening people for having this disease or not. So one option for us is to screen all the people of a city or a country, and that would be a really Herculean task. So instead what has been done is to use the thermal screening, where the body temperature of the people coming to say airport or railway stations is being measured through thermal detectors, and those who are showing abnormally high body temperatures are being considered to be suspect cases. So when we say again here abnormally high, we are implying now the right side of the tail of the Gaussian curve, and presume again that about 2.5% of the people will actually have a higher temperature reading. So the question arises, what is the utility of undertaking this thermal screening? So if you see that the prevalence of the disease is 0.1%, so for finding one actual patient we will have to screen 1000 people on an average. But if we can pre-screen the people based on their temperature rise, we will have a 4% chance of finding the people with the disease. So we essentially increase our odds of having the patient or finding the patient significantly from 0.1% to 4% just by using the increased body temperature as a pre-screening parameter. Now we can also discuss what are the errors that we can commit in undertaking this exercise. So we can also discuss the null hypothesis here in this context. will be that anyone who is screened is not having the disease. Now, type 1 error in this context would be what we call as the false negative, that is when we reject null hypothesis when it is true, and that would imply detaining all the people showing increased body temperature. So obviously, as we can think that just because someone has a high body temperature does not mean that the person is actually diseased, but we are increasing our odds of finding a person who has the disease by undertaking the thermal screening. Similarly, the type 2 error in this case would be letting go a diseased person because, say, they are not showing the symptoms or they still do not have high temperature onset. So, this again is a very a real possibility to happen. So, if I draw a Venn diagram of this situation, this is the whole population that we have, and suppose we have the diseased people or the people who have the disease being represented by this red region. What we are essentially doing through thermal screening is shown in the blue profile, where we are essentially increasing our odds of finding the people with this disease. We will have a greater probability of finding the people who have the disease, but we may still commit a type 2 error in cases where the thermal screening will be unclear or ineffective. Now, we can also think of what all are the various sources of error that may arise during the thermal screening. So, this part I leave to you to think and figure out what could be the sources of errors that may come when we are screening patients for their high body temperature through thermal screens. So, essentially what we covered in week 4 was the utility of the z-test, the t-test, and we also got introduced to the f-test for comparing the precisions, and also the q-test for finding the outliers. In a data set. So, this essentially set us well for the next week's discussion, which was on what is known as the analysis of variance, or in short Anova. Now, the analysis of variance that we discussed in this course was known as the single factor Anova. That means we have been dealing with only one variable in this. Now, as discussed in week 5, this variable can be temperature, the variable can be the person who is conducting the measurement, or any other variable that we can think of. For example, pH can be another variable, and we had essentially three things here. One, of course, is the factor which is being varied, and then we had levels. That means how the factor was varied. For example, if the factor is temperature, then the levels will be the various temperatures at which a certain measurement was repeated. So, the factor, if it is temperature, then the levels will be T1, T2, T3, T4, and so on. And then we have the response. For example, this response could be the yield of the reaction or the enantiomeric excess, for example, and what we will have to do is to perform the reaction at a particular temperature T1 for multiple times. So, the change or the differences in the enantiomeric excess within a temperature value will be compared with the changes or in the enantiomeric excess at different temperatures T1, T2, T3, T4, and so on. So, based on all these, we will be creating what is known as the analysis of variance table. And here essentially we saw that we enlist the source of variation, then we talked about the sum of squares, the degrees of freedom, and finally the mean square values and the F calculated value. And in the source of variation, we could have two sources of variation, what we call the between the groups, which is known as the factor effect, and also within the group, which is known as the error effect. Consequently, we have the sum of squares due to factors, which is enlisted here, and the sum of squares due to errors. The degrees of freedom in these two cases are different. If we are dealing with I number of sets or I groups, then the degrees of freedom for the factor effect will be I minus 1, and for the sum of squares due to error, the degrees of freedom is n minus I. Now, from this we can calculate the mean square factor, which is nothing but sum of squares factor divided by the degrees of freedom I minus 1, and the mean square error, which is the sum of squares due to error divided by n minus I degrees of freedom. From here we calculate the F calculated value, which is nothing but MSF divided by MSE. And we can also do a total value here. So this will become SST, which is nothing but the sum of SSE and SSF. The degrees of freedom total would be n minus 1 if we are dealing with a total of n readings. So once we create this Anova table, we get a F calculated value, which is then compared with a F critical value. So F calculated is compared with F critical value to estimate or to infer whether the H naught or the null hypothesis holds true or not. At a particular confidence level. Now F critical we estimate by taking into consideration the confidence level value and the I minus 1 degrees of freedom for the numerator and n minus I degrees of freedom for the denominator. Now once we have a F critical value which is less than the F calculated value, then we reject the null hypothesis and at this stage we can only say that at least 2 or more groups of the given data set are having results which are significantly or means which are significantly different from each other. To understand or to quantify which of the groups are actually having a difference, we use what is known as the least significant difference and we calculate this least significant difference value as t square root 2 into mean square error by ng, where ng is the number of replicates in each group. The t value here is having a particular confidence level value and the degrees of freedom are the same as that for the error, which is n minus I. So from here we calculate a value of the difference between the means which is considered to be least significant at a certain confidence level, and from here we can estimate which of the groups are actually having different mean values between each other. Now once we have done all this exercise, week 6 and week 7 were essentially devoted to the concept of data fitting and using different models to fit the data and estimate the parameters that require to be estimated, and Dr. Bharadwaj Satyamurthy covered this for both linear data fitting as well as the nonlinear data fitting.